Okay, thanks very much. Hi. So yes, I'm a professor at University of Hawaii, but for 20 years, a little over 20 years, I've also had an affiliation with the Software Engineering Institute. And in that collaboration with them, I've authored a number of books on software architecture and related topics. The most famous book, I guess, is called Software Architecture in Practice. And we really believe in that in practice part. So everything that I'll talk about today, everything that we talk about in our research and in our presentations is tested in the field, is tested in practice. So even though I work at a university, I'm not a theoretician. I always believe that this being an engineering discipline, you have to really try out your techniques on real projects and real world situations to know whether they work or not, and to understand the affordances. So I'll be giving you what I'm calling a gentle introduction to software architecture. And there's many courses and books and materials and papers and so forth that go into much more depth on each of these topics. So we're just going to be skimming over the tops of the mountain peaks today, but hopefully that'll be okay. So let me just share my screen here. Okay, hopefully you can see that. Good.
Yeah, I can see it. Yeah.
Great. So the Software Engineering Institute for years has maintained an area of its website which includes information about software architecture and definitions about software architecture. In practice, software architecture, if it is ever documented at all, is box and line diagrams. There's boxes that show the parts of the system, and there's lines showing some relationship among those parts. So we see pictures like this with lots of boxes and lines, and maybe the lines have different shapes and thicknesses, and the boxes have different coloring. But sometimes we see even more idiosyncratic relationships and shapes, and these come in all sizes and shapes, all forms. Sometimes they have a legend, which is nice. Sometimes they don't. Sometimes they use a known notation, such as UML. Most often they don't. This was an example provided to us by a customer who we were doing some work for and trying to analyze their architecture. And this was the diagram that they provided. So what can we tell from these pictures? What's the good of them? Are they just wallpaper? Or do they actually provide some knowledge and some insight? So you can ask about the elements of the picture. Some of them, let's go back to this last one. Some of them are adjacent to each other. Some of them are separated by lines. What's the significance of that separation? Do these things exist at runtime? Are they code units? Are they units of packaging or deployment or something else? Are they processes? Are they programs? Are they hardware? Are they objects? Are they tasks? Are they threads? Are they, right? What are they? Frequently, we don't know. And what are the responsibilities of each of these elements? Sometimes you can tell by looking at the words in the diagram, like access control or access logging service or database abstraction layer, but sometimes not. If you look in the middle, you see shop quick and easy op. Who knows what those are? So what do each of these elements do? We don't know. What about the connections between the elements? Do they communicate with each other? Do they control, send data, invoke, synchronize? Do they run at the same time as each other? Or are they mutually exclusive? Are some of them replicas of others, let's say for redundancy or fault tolerance? And finally, what's the significance of the picture's layout? Some things are closer together than other things, right? All of us, all humans, are visual information processors. We expect that adjacency means something in a diagram. For example, So I don't know if you guys are familiar with this expression, but we often say a picture is worth 1,000 words. And in software architecture, we say that pictures like this are the ones that require 1,000 words or 10,000 words because there's so much left unsaid. So the picture itself is not an architecture. Let's start with the definition. This is the definition that comes out of our book, Software Architecture in Practice. So the software architecture of a system is the set of structures needed to reason about the system, which comprises software elements, relationships among them, and properties of both. So first of all, there are other definitions of architecture that we stand in opposition to, that we'll talk about the architecture being the early design decisions or the major design decisions. And while that may be the case, that architectural decisions may be early or major, there are some architectural decisions that are made early that are not architectural. Sorry, some decisions that are made early that are not architectural. And there are some architectural decisions that are made late. So we don't like those kinds of definitions. But if you focus on the structures, that an architecture is about the structures of the system, their elements, their relationships, and the properties of those, then you can really start to reason about an architecture, because an architecture is an abstraction. It's about elements and relations and their properties. Why do we use abstractions? Well, we need them to manage complexity, right? I don't know about you guys. I'm not a great programmer. I'm okay. So maybe I can keep 10,000 lines of code in my head, really understand them, really know what's going on in those 10,000 lines of code. Maybe you guys can keep 50,000 lines of code in your head. I'm prepared to believe that there are people who are 5 or 10 times better than me at that. But what's the biggest possible system? How many lines of code is the biggest system? And there's no answer to that, right? It's millions of lines of code. If you look at Chromium or Linux or systems like that, there are tens of millions of lines of code. So nobody can keep all of that complexity in their head. Even if they once knew it, they won't remember it all, right? We're imperfect information processors. We're biased. We have tension issues. We sometimes forget things that we previously knew. So we need an architecture to abstract certain details, to intentionally omit certain details, and focus on the elements of the system, how they're arranged, how they interact, how they're composed, so that we can reason about the properties of the system. How will these elements, when working together, perform? If I have a fault in one of these elements, will that fault propagate to other elements? If I modify one of these elements, will that cause me to need to, or likely need to, modify one of the other elements? These are architectural principles, architectural kinds of reasoning. So what do we mean by properties? Well, properties are assumptions that one element can make of another element. So for example, if you're worried about the performance of the system, I might be worried about how much of the CPU or how much memory a particular component consumes, average case or worst case, so that I can now reason about the composition, maybe a pipeline or a series of these components that work, a set of these components that work in parallel, to reason about the potential worst case latency or worst case throughput of the system. But properties may be other things, like how something handles faults, or how resilient it is to faults, or how it uses some other shared resource, the database, buffers, threads, anything. So when we talk about the elements of a system, each element has an interface, and that's more than just an API, right? It's all of the stuff that's on the public side of this public-private partition, all of the stuff that you need to know about that element to reason about it without having to know how it's implemented or all the details of its implementation. So architecture is concerned with the public side of that public-private division that is mediated by the interface. And again, by interface, I mean much more than just API. Another implication of the definition is, we said it's the set of structures consisting of elements and relations and properties. So no system has just one structure. Even Hello World has more than one structure, right? Because there's Hello World as a unit of code that maybe I keep in my GitHub repo. There's Hello World that I compile into an executing process. That's different than the code. It's a process. And then I allocate Hello World onto some processor for execution. And how quickly it executes may depend on what else is going on that processor. Is that processor already overloaded, right? I can't even reason about the performance properties of Hello World in isolation. I have to understand how it's allocated onto hardware for execution. So if anyone ever shows you a single picture and says, this is the architecture, they're either lying, or worse still, they're naive. They don't understand. Because there's no way you can reason about the properties of a complex system, at least by looking at any one picture. So every system has multiple structures. You may choose to document or reason about different structures, so the set of structures isn't fixed. The relationships between them may be runtime relationships, A calls B, or they may be non-runtime, A inherits from B, or A depends on B, A calls B. Also, architecture includes behavior. So it is often the case that you need to understand how elements interact with each other, that aspect of their behavior, something that you would capture perhaps in a sequence diagram, to understand the emergent behavior of the whole system. So when you see box and line diagrams, they may have some of this information, but often you're left to fill in the gaps, to imagine the functionality, to imagine the behavior, to imagine properties like the performance characteristics or their modularity characteristics. So these box and line diagrams rely on information that isn't there or that may be wrong. And we'll see how this can have negative consequences very, very easily. Now, this doesn't mean that you need detailed specifications for every element of your system. That would be burdensome. What I'm worried about is the carriers of risk. So if I have one part of the system that only executes rarely, that it doesn't use much resources, that it's a dark, seldom used corner of the system, maybe I don't document that. Maybe I don't reason about that. I want to reason about the core of the system that is providing the core functionality, the important use cases, the important failure cases, so that I can reason about the things that may be carriers of risk in the system. So we only document behavior if it affects the system as a whole. And by that, I mean it affects an important property of the system, such as its latency or its mean time to failure or mean time to recovery. Another implication of the definition, set of structures, is that every system has an architecture, because every system is composed of elements and there are relationships between them. Even Hello World has an architecture. It has one element related only to itself, but that fits the definition. However, having an architecture, every system has an architecture, is different than having an architecture that is known, that is documented. Maybe the people who designed the architecture are gone. They've left the company, they've moved on to another career. Maybe the documentation has vanished or never existed or is completely out of date. to what extent, if there is documentation, does the actual code base relate to or comply with that documented version? And even if we know all that, do we understand the rationale for architectural decisions? Do we understand why a particular decision was made? If we don't, then it is possible and maybe even likely that at some point that architectural decision will get undermined, right? The analogy I like to use is if you build a house and then you allow plumbers and electricians and heating and air conditioning people to start drilling holes in the walls wherever they like to put their pipes and their conduits through there, you may be undermining the structural integrity of the building. The building may fall down because you've drilled too many holes into a supporting structure within the building. And that's exactly what happens all the time with architecture. This is why technical debt accumulates, another topic that's near and dear to my heart. So if you don't explicitly develop an architecture, you will get one anyway, but you might not like what you get, and you frequently don't like what you get, and you certainly won't like it over time as it evolves. Let me give you a quick example, a simple example from my own experience. So this was a system that I developed quite a few years ago with a graduate student of mine. So this was a little research system. We were trying to build a system that had 5 layers, essentially. And the idea was that we were building a flexible visualization front end for this system. So we had a presentation layer, which was implemented in a UI toolkit. And we had a functional core. That was what the system did, its essential function. And then there was a dialogue. So you can think of this like model view controller, where the controller is the dialogue that mediates between the functional core and the presentation. And then we had these 2 adapter layers, a functional core adapter, which would allow us to change the functional core. It would be like if you wanted to swap out your database for a different one. And a logical interaction adapter, which would allow us to swap out the user interface toolkit if we wanted to. So we had these 5 layers, and this was a user interface model that was popular at the time. We just adopted it and implemented it. This was our architecture, or at least one aspect, one view of our architecture. So there was just 2 developers, me and the grad student, and that really meant 1.1 developers because the grad student does most of the work, right? And at one point, we reverse engineered the system. And what we found was that we had violated our own architecture. There were connections, dependencies directly between the functional core and the dialogue, and directly between the presentation and the dialogue. This is the best case, right? We're architecture people. We believe in architecture. And we used an architectural pattern that was documented, and we implemented it, and we still got it wrong. So what are the chances that your architecture violates its intended design, if in fact one was created, if in fact one was documented? And I can tell you the chances, and they're nearly 100%. And that can have negative consequences, right? These extra dependencies actually have consequences. It means if you change one of those things that are meant to be swappable, they're not swappable anymore because you've got these extra dependencies that you didn't count on. The cleanliness of the abstraction has been broken. So box and line diagrams are good, but they're just a starting point. We need to add more information, specification, properties. We need to connect those diagrams to the code base, to the real ground truth artifacts to ensure that we're compliant with them. And if we're not compliant, we either should change the implementation so that it complies, or change our rationale, or change our documentation, right? If you were building a house, the planning board that approves your building permit wouldn't allow you to submit one thing to build and then to actually construct another thing. It's unthinkable in the world of civil and structural engineering. Unthinkable. But we do it all the time in software engineering and software architecture. Finally, the definition is indifferent about the quality of the system. Is this a good or bad architecture? Don't know. We just say in the definition that it's a set of structures, elements, and relationships and their properties. You now need to do some additional analysis to figure out whether that architecture meets its functional requirements. That's the thing that we usually cover pretty well, right? That's why we write our test cases. But it's quality attribute requirements, how well it performs, how testable is it, how resistant is it to faults and failures, its availability requirements, how secure is it, how integratable is it with other things, how evolvable or scalable. All of these IEEEs are going to really be the carriers of the quality of the system. They're going to determine if your system will be a success over the long term. So why is architecture important? You may all recognize this picture, the Sydney Opera House. The Sydney Opera House, when it was built, was finally produced about 10 years late, according to their original schedule. And I think it's 13.5 times over their original cost estimate, right? And we hold this up as an example of wonderful architecture. And it is. I've been there. It's amazing. But the architects had a huge struggle. They were pushing the envelope of what was possible. And when you're pushing the envelope, it's hard to achieve predictability. Fortunately, most of us are not building the Sydney Opera House in our software, right? We're building things that are quite similar to things we've built before. And so we should expect and demand more predictability. So in particular, we should demand predictability about these quality attributes. So if the only criterion was to compute the right thing, almost any architecture would do, right? Given these inputs, we get those outputs, done. But other stuff matters, right? These IEEEs, these quality attributes, they matter, and they matter just as much to the long-term success of the architecture. And they are orthogonal, they're independent from what it is the system does. So I could build a system to do, I don't know, payroll processing. And that system could be fast or slow. It could be reliable or unreliable. It could be easy to maintain or difficult to maintain. And there could be trade-offs in there. If I make the system a little bit more secure, I sacrifice some performance. If I make the system easier to port between platforms, maybe I make it less easy to scale. So all design involves trade-offs. And this is true in every domain, not just software, right? The design of the tires on your car are a trade-off between, you know, how well they work in the wet, how well they work in the dry, and how well they work in the snow, and how long they're going to last you, how many kilometers they'll last you. All design involves trade-offs. So the earlier we reason about these trade-offs, the better. So there's 13 reasons that we talk about for why architecture is important. First of all, an architecture will enable or inhibit the system's important quality attribute requirements. So if your system was not designed with some performance requirements in mind, if you haven't architected for performance, it's going to be, it may be at least, very difficult to achieve those requirements. If your only answer to meeting your performance requirements is we're going to hack until it's fast enough, then you may not be able to achieve those performance requirements, or you may not be able to maintain them as the system grows and evolves and gets more complex. This is why systems often get retired, because they can no longer meet their quality attribute requirements. Architecture allows you to reason about and manage change as the system evolves. So if a system is just allowed to accumulate complexity with no attempt to control it, with no attempt to manage it, it just becomes a tangled web of dependencies, a big ball of mud. And eventually, again, the system gets crushed under its own weight. You can analyze architectures. This is the good news. You can analyze representations of an architecture early on or you can reverse engineer those representations from an existing architecture. And this allows you to predict a system's qualities. And I've got lots of examples of doing this. If you document the architecture, this really helps when stakeholders are communicating with each other, right? You are communicating at a higher level of abstraction, which allows you to talk to each other about the properties of elements without having to understand all of the details. And this is a huge win for communication. As I mentioned, the architecture is the carrier, is the embodiment of the earliest, most fundamental design decisions, which are the hardest to change. You know, is this system going to be structured as client server or peer-to-peer? Oof, I don't want to change that partway through the implementation, right? So those early fundamental decisions are woven into the very fabric of what the system is. An architecture defines a set of constraints on implementation. This is how any component gets resources and releases resources. This is how a component reports a fault or manages a fault or recovers from a fault. This is how a component communicates with another component. These kinds of rules can be established architecture-wide, and then the architecture is less likely to become that tangled big ball of mud. An architecture dictates the structure of an organization. So this is called Conway's Law. And this was first noted by this guy, Melvin Conway, back in 1967. There he was working with an organization that developed compilers, and he noticed that if there was a 3-phase compiler, they had 3 teams. And if there was a 4-phase compiler, they had 4 teams. So there's this mirroring or paralleling between architectural structures and organizational structures. And you can use this to your advantage, or you can let it dictate your architecture. An architecture can be the basis for evolutionary prototyping. So as I'm designing my architecture, I can identify risk areas where I don't know enough, where I don't understand the performance characteristics or scalability or availability or some other characteristic. So I can prototype those areas, and based on the results of that prototyping, evolve the architecture. Architectures help us reason about cost and schedule. So one technique that's really useful is to have an architect, based on their architecture, do a top-down cost and schedule estimate. So based on my architecture, here's what I believe it should be. Then you can hand out the components of that architecture to individuals or to team leads and ask them to do an estimate for each of their pieces. That's like a bottom-up architecture estimate. You then compare the top-down and the bottom-up, and you resolve any differences. And that, what we call a consensus cost and schedule estimate, is much more accurate than either the top-down or the bottom-up alone. Architecture can be the heart of a product line. So if you are creating really useful assets and a really useful architecture, why not tailor it, parameterize it, so that you can create many systems out of those same assets, appropriately tailored and parameterized. Architecture allows you to focus on assembly of components because, again, we're concerned with the public side of that public-private definition. So we want to treat components as black boxes with properties. And this means that you can think about buy versus build decisions rather than simply assuming you're going to build everything. Also in architecture, by restricting design choices, you actually free up the attention of your developers to focus their creativity within the bounds that they've been given, right? You give them a box and you say, this is your box, do what you will with it, as long as you comply with the interface specifications. And this is a kind of divide and conquer process that allows systems of unbounded complexity to be built. Also, the architecture or a documentation of it can serve as the basis for training a new team member. So why should you document an architecture? Everybody hates documentation. I hate documentation. You hate documentation, right? But here I'm going to make an argument that you should document something. The documenting nothing is the wrong strategy. And we say there's 3 reasons to document an architecture: for analysis, for construction, and education. It makes a nice acronym, ACE. So this does not mean you need to do heavyweight documentation, that you need to document everything, but you should ask yourself, if I'm going to need to analyze this, if I want to control how someone constructs this piece downstream, or at least guide them, and if I want to educate a new person on how this works, then maybe I should consider documenting at least the most important design decisions made. One time, the very first time I did a architecture trade-off analysis, this was back when we created a method called the architecture trade-off analysis method. The very first time I went and did one in industry, I got there and I was interviewing the team members and getting to know them. And every time I asked what I thought was a hard question, they said, Cal knows the answer to that. Ask Cal. Cal can tell you about that. And Cal was away that day. And that got me thinking, what would happen if Cal got hit by a bus? Right? This project is in deep trouble if Cal got hit by a bus, because all of the important decisions were apparently in Cal's head, and that's a risk for a project. So we document to mitigate risks. And it might just be that we're documenting 10% of the system. It, again, doesn't have to be heavyweight. When should you document a system? Well, as you're designing, as you're making a decision. If it's an important decision, if this decision has non-local consequences, you should document it. This speeds up documentation. It reduces the burden. In fact, I will argue that it's impossible for you to design without documenting. I can't design without standing at a whiteboard and sketching, or sketching on a piece of paper, or opening up, my favorite drawing tool. And so why not just capture that? If it's a whiteboard sketch, take a picture, upload it to your project wiki, add a few words of explanation about what each of the components are and what are their relationships and what are their properties. Done. So at the very least, you should provide a legend that says what an element is, what are the boxes, and what do the lines mean, right? There's so much confusion that avoids, unnecessary expenditure of effort if you do that. How should you document? As a set of views. Each structure can be viewed as a view. And so this allows us to think about architecture, to divide up architecture into coherent representations of the system. So let's say as a set of code units, files that I store in my GitHub repo, that I store as files in my file system, as a set of directories. That's different than a set of processes that are executing on a processor, or a set of containers that I've allocated to a cloud instance somewhere. And so I should document those separately. They've got relationships, but they're different things inherently. So you need to document the relevant views, the ones that are important carriers of quality, and then the documentation that applies to more than one view. If I'm trying to do continuous integration, I need to know when I make a change to this component, how that gets tested, how that gets compiled into some sort of executable and packaged, maybe containerized, and then deployed, maybe onto a sandbox, maybe onto a pre-deployment infrastructure, and then from there into production. So I would want, so that's a journey, right? From change of one line of code to one module all the way to production. I would like to understand the relationships between those, so that when I make that one line of code change, I know what else is affected. I might know what else to test or to inspect. So we sometimes call this views and beyond, right? Because you have these views of the architecture, but then you have to knit them together with additional information. So if you think about the human body, doctors have a set of views that they use to understand the human body. If you're a neurologist, you have one view of the human body. If you're an orthopedist, a different view, or a dermatologist, a different view, or a cardiologist. So some of these views are focusing on specific subsystems. Podiatrist worries about the foot and ankle and the lower limbs. Ophthalmologist worries about the eyes and the connection of the optic nerves. And so different physicians are dealing with parts of the body that are related, but they're focusing on different properties, on different structures. Even though everything in your body, you only have one body, everything's interrelated, these specialists focus on different aspects. These together, all of them together, describe the architecture of the human body. And it's exactly the same with software. So no one view of your architecture is going to suffice, right? If I go with an EKG to my dermatologist, they're going to say, this does me no good. An EKG doesn't tell me anything about your skin rash, right? So different views, different analyses for different purposes. So again, set of structures, no one structure is the architecture, but the important ones that we tend to want to document are module views, component connector views, and allocation views. So which ones should you document? Well, you should document the ones that you need. What are the important risks in your project? If your project, for example, has very, very trivial, simple performance requirements, you're just building an app, the app isn't particularly CPU hungry, maybe you don't want to build a component connector view or an allocation view because you're just not that interested. It's not important, it's not complex, but maybe your app has a lot of parts and pieces, a lot of modules that depend on each other, and it's changing all the time. And so maybe you want a module view. You want to document the modules in the system and how A calls B, A inherits from B, A uses B, A relies on B doing something. So I can't say document this and this, and you will meet your needs. You document the views that are going to be the carriers of important qualities that you care about. Every view has a cost and a benefit, and so you should ensure that the benefits outweigh the costs. So module structures are where we think about implementation units, modules, files, and this tells us how the system is structured as a set of code units. And we typically assign modules to individuals or to teams for implementation. And so this may cause us to annotate it with information like, does team A even talk to team B? And should they talk to team B? So the elements might be classes or layers or other divisions of functionality. And at this point, we're worried about the functions of the system. We're not worried here about how that is manifested at runtime. So this helps us answer questions like, what responsibilities are assigned to each module, right? If I want to change this function in a system, what file or files do I need to go in and modify? And if I do so, what other files may be implicated? I was working with ABB, the Swiss engineering infrastructure company, a number of years ago, and analyzed a bunch of their systems. And one system they said was so bad, had so much technical debt, that if they wanted to change one line of code, they had to budget a person month of effort. One line of code. And that's because they did not know when they changed that module what non-local consequences that module had. They're component connector structures. So this is how a system, the elements of a system interact. If you only see one picture of an architecture, it's almost always a component and connector structure. If somebody shows you a picture and says, this is my architecture, it's a component connector, or what we call a CNC structure. So these components are runtime entities like services, and the infrastructure that those services execute within and the relationships between them, how they interact with each other, how they send messages to each other or events to each other. So this is going to allow you to reason about runtime behavior and the interactions between the piece. You know, is it likely that this component is going to get overloaded with requests? And if so, maybe I need to create additional instances of that component. But is that component stateless or is it stateful? And if so, then maybe I need to think about externalizing the state. And, you know, these kinds of reasoning decisions are what you do with CNC structures. So the elements are services, peers, clients, servers, filters in a pipe and filter system. And the connectors are call return, remote procedure call, pipes, event buses, and so forth. And so you reason about runtime properties with these structures: performance, security, availability, energy efficiency. Ooh, there's one we don't often think about, but it's getting to be increasingly important. And finally, there are allocation structures. And this allows you to reason about how something in a module structure or a CNC structure is allocated onto something in the real world. And that may be, for example, how software is allocated onto teams for development, or how containers are allocated onto server instances for execution, right? So that we allocate different things from those module and CNC views onto different things in the real world. So, well, I just made those 2 points. So which structures are architectural? Well, mumble. A structure is architectural if it supports reasoning about some important system property that you care about. That's it. That's it. Am I worried about this? Is it keeping me awake at night? Then I should probably document it, and I should probably reason about it, and maybe have design reviews about it, and maybe monitor the system, the code, or the system at runtime so that I can measure it and see how it's changing over time. So these tend to be quality attributes that are important to some stakeholder of the system. Some stakeholder, right? So a tester is concerned with testability. An end user is interested in the functionality, of course, but also the performance. Is this thing responding to me appropriately? A operator or facilities person is interested in security and availability, keeping the system up and running and healthy and free of intruders. So there are many different ways in which a stakeholder might be concerned with a different property of the system. And if you neglect some of those stakeholders, you introduce risk into the system. If you think that you can hack your way out of it, well, maybe sometimes that works, sometimes that succeeds, but it's not engineering and it's not sustainable. It doesn't work very well as system complexity increases. Oh, and finally, architecture. So it's typically a one-page informal description of the architecture. It may show some major components and relationships. It violates all those rules that I told you. It typically doesn't have a legend. You can't reason about it, but it's important often for communicating with non-technical stakeholders. So it's a starting point for discussion. So don't sneer at it. It can serve your purpose from time to time when you're trying to sell your vision of the architecture. Okay, so what makes a good architecture? I'm almost done. So there's no such thing as an inherently good or bad architecture. All we can say is architectures are more or less fit for some purpose, right? If my architecture is an ungodly mess and unmodifiable, but I don't ever intend to modify it, no problem, right? It is said that the original hyphenation algorithm in Microsoft Word was written by Bill Gates. And for years and years, nobody touched it. Nobody understood it, but it worked, right? So was that unmodifiable clump of code a problem? No, it was not a problem. It worked and it didn't need to be modified because it worked, right? So we should not assign arbitrary metrics and say the system has to be, at this level of quality. It has to be at this level of quality with respect to specifically stated goals, goals that we elicit from our stakeholders or that we infer from our stakeholder needs. However, there are some rules of thumb. You should have a single architect or a small group of architects. Architecture does not emerge bottom up, sadly, right? It would be like you've got to build a 20-story office building downtown. You don't just send in plumbers and electricians and carpenters and say, start pouring concrete, start welding, right? You're never going to get a coherent 20-story office building that way, right? You need to have a vision. You need to analyze the design for specific properties, which means that you have to, the architect or architecture team has to base their decisions on a prioritized list of quality attribute requirements. Is performance more important than modifiability? Is modifiability more important than performance? I might make different decisions, different trade-offs based on those. So specifying the requirements is important. Understanding the relative priorities is just as important. Document the architecture using a set of views. And again, this doesn't have to be heavyweight. Just document the really important stuff, the stuff that if somebody undermines that decision, we're in trouble. You should evaluate an architecture, right? Would you deliver code that you had not tested? Of course not. But we deliver architectures that we haven't consciously documented or analyzed all the time. I do a lot of analyzing of systems for technical debt, reverse engineering of systems to understand the state of the architecture. And most systems are a mess if they've been around for more than a couple of years, right? That's just the state of the practice. It's sad, but it's true. An architecture should lend itself to incremental implementation. If you want to do this, what this means is you should develop a skeletal architecture, sometimes called an architecture runway, and then incrementally add on to it. So this is becoming a more and more familiar and popular approach in the community of agile architecture, where people will talk about things like a walking skeleton, right? It stands up, it can walk, but there's not much meat on the bones, and we add that meat as the system evolves. You should think very hard about information hiding and encapsulation and abstraction when you're defining an architecture, because the degree to which a system is decoupled, the degree to which the components of a system are not tightly coupled to each other, is going to affect how easy it is to modify, maintain, change, evolve, integrate, scale, and probably I'm missing a few other qualities in the future. And you should design your architecture using proven patterns and tactics, right? Yes, the Sydney Opera House required the architect to define whole new ways of building. They were pushing the envelope. Most of us are not building the Sydney Opera House. As I said earlier, we're building much more precedented systems, and so we should stick to tried and true proven patterns and tactics. Other rules of thumbs. Executables should be written so that it's easy to change their environment even at runtime. Also at runtime, thinking about runtime, you should identify resource contention areas, right? Are we worried about running out of memory? Are we worried about overloading the database with requests? So what are the areas of resource contention? Let's think about those and reason about those, and maybe set up budgets for those, or do a prototype or instrument a system so that we can take measurements, right? This is engineering. Architecture should feature a small number of ways for components to interact. So it should be the case that there are a small number of ways to do anything in the architecture, ideally one way. This is how I report a fault. This is how I initialize. This is how I query system state. This is how I change the system state, and so forth. And this is going to dramatically improve the understandability of the system, reduce development time, increase reliability, enhance modifiability. Finally, tools can help. Architectures are complex. And it is often the case that what started off as a decent, well-reasoned, well-imagined architecture has descended into insanity because of, it's death by 1,000 cuts, because of every developer making a change doesn't realize if and where they're undermining the architecture, just like that electrician drilling into the wall, right? It's only one little hole. What? How could this hurt anything? One little hole in one little wall, right? But over time, that technical debt accumulates. So there are tools. I did an evaluation of technical debt detection tools last year, and one in particular stood out. It's called Deviate, which this tool really was useful in helping to reverse engineer and identify architectural flaws. So we're done. Just to summarize what I said, architecture is the set of structures needed to reason about the system, which comprise elements, relations, and properties. A structure is a set of elements, and structures represent the primary way that we reason about an architecture. This is what gives us engineering control or leverage over architectural decisions. Every system has an architecture, but that architecture may not be known, it may not be documented, the as implemented system may not be the same as the as designed system. And there's no such thing as an inherently good or bad architecture, but we need to reason about them nonetheless, because architectures may be more or less fit for our purposes, for our needs, for our requirements. So with that, thank you, and I'm happy to take questions.
Thank you, Rick. So as always, it's very insightful. I've seen a lot of your presentations before and courses on software architecture, so thanks a lot. One of the users told that my microphone was a little bit low. Yours was well. So can you hear me now well?
Yes.
Okay, great. Yeah, perfect. So it seems that everything is okay now. So there were pretty good discussion in the comments, and there were 4 questions. I'll read them now. And yeah, so the first question was basically how to find the middle ground when creating architectural documents. So basically, it's obvious architectural documents should save money and costs of maintaining these documents. Should be lower than benefits of having architectural documents. But in the real world, there are so many unknowns, and sometimes it's very hard to decide, should we add more details to the documentation or not?
Yeah. So, I mean, we teach a whole course on architecture documentation, so I'll just give the quickest of answers to that. But again, go back to analysis, construction, and education. If you can identify a need to document a piece of information because you may want to analyze an architecture, and that analysis will require that information. If you are concerned about the construction of the system to comply with that specification, or if you need to educate someone on that aspect of the system so that they come up to speed more quickly, then it sounds like you have a need to document that architectural decision. Or to put another way, that there would be a risk, a future potential loss if you did not document the system, right? Because what's the alternative? New guy comes onto the project and you say, ask Cal. For every decision, ask Cal. Cal knows that. And it means it's going to be 18 months until new guy is actually productive and independent. And new guy doesn't know what he doesn't know. So that's a risk. in a complex system.
Yeah, that makes sense. I totally understand that. And basically, in our service business, where we basically build the software systems for other companies, for our clients, we often face the situations when the client says, hey, it takes us 8 months to onboard a new engineer so that this person starts being productive. And I'm thinking like 8 months, that sounds like too much for an engineer. So it looks like there are problems with documentation or other things. I mean, so yeah, that makes sense. Thanks.
I wasn't making up the 18-month number. One system I worked with, that was their claim. Their system was so complex and not at all documented that it was 18 months from the time they hired a new person to the time they expected that person to be productive.
Yeah.
So it could have been worse than 8 months.
Okay, so thanks for that. So the second question is, you mentioned documenting architecture, and there are no doubts architecture is important. How about validations of architecture? So early stage decisions influence the cost of all products. What, in your opinion, is the best approach to early stage architecture validation? Of course, in an agile environment where we can start with shelter and it may become an opera house after some time.
Yeah. So I think you need a process of strategic prototyping. So I actually wrote a paper about this a few years ago, and I can share that paper with you. But basically, the idea is that there's a set of questions that you need to ask yourself about how precedented or unprecedented are our requirements. Are we dealing with new tools or new technologies? And so forth. There's a set of questions. And if the answer to those questions is yes, then you probably need to build a prototype. And now the question is, do I build a throwaway prototype or an evolutionary prototype? Right. And so if the question that you're trying to answer is very narrow, then a throwaway prototype is often the least expensive way of getting an answer to that. You know, how many simultaneous requests can I throw at this server before it starts the latency, the latency starts to go asymptotic, right? So maybe you don't know that until you've built a little prototype. You throw requests at ever increasing numbers at this component and you measure latency, right? And there may be no other way to know it than that. So in that case, you want to do a throwaway prototype. There are other cases, however, where you may need to do an evolutionary prototype when you're asking bigger questions about the system that involve taking a system and then tweaking it. And, you know, we'll try option A or option B, and then maybe we do A/B testing or canary testing or something like that to validate it. So the point is you need to be strategic about your prototyping to answer these questions. There's no one size fits all, and it's going to depend on your context and your risk.
Okay, that makes sense. Yeah, thank you. So two more, much more than two, but yeah, limited. So basically, is there a way to define what development methodology to use based on the architecture documents? So would it be based on the work allocation and module views or another ones?
I'm not sure I understand the question.
So basically, the question about like development methodology. So is it like Scrum or Kanban? Is it possible to use? Yeah.
Got it. Thank you. Yeah. So what we found is that it's orthogonal to development methodology. Architecture doesn't really care about the development methodology, or maybe I'll say it in a positive way, interleaves equally well with any development methodology. So we've worked with teams doing doing, well, Scrum tends to be the most common, but other development methodologies, even doing waterfall, older government projects, for example, tend to be waterfall. And the way that the points at which you can make architectural decisions may change. The need for strategic prototyping may change, or it may happen at different points in the life cycle, but it seems like it's equally well suited. If you think about agile methodologies, you want to be responsive, you want to be risk driven or responding to risk, and that fits very nicely with the architectural principles of only document what you need to document, only analyze what you need to analyze, figure out what your important drivers are and focus on those, prototype those. So it seems pretty process agnostic to me.
Yeah. Okay, thanks. Yeah, that definitely makes sense. Yeah. So one more questions. Just a second. It often happens that we cannot predict business future needs and requirements when we create architecture. Of course, we want to do our best and build a scalable system, gather requirements, etc. But do you think it makes sense to try to predict how the system is going to scale and grow, and consider that in the architecture creation?
Yeah, I mean, this is a really tough problem. It's never going to be easy. So what we typically do is when we elicit architectural requirements, we ask for three kinds of requirements. One is the functional requirements. I know, this is a cash machine. I know it's going to have to dispense cash and allow me to make deposits and transfer money between accounts. There's certain things I definitely know the system's going to have to do. Then there are quality attribute requirements. And we, again, may know some of those, like I want to be able to dispense cash and the latency should be no more than 30 seconds. Otherwise, people start to get uncomfortable. So those are, again, the expected or known requirements. Then there's exploratory requirements. What if we triple the number of cash machines out there? What if we go to 10 times the number of cash machines out there? What would be the effect on latency and throughput in our system? So we typically try and capture some of those because those are architectural test cases. And then we'll ask for exploratory requirements. So that's where you're really considering more far-ranging changes. Not that we expect any of these to happen immediately, but we want to understand what would the consequences be on the architecture. Would this be a total rewrite? Would we simply have to change a couple key decisions and the rest of the system would be okay? So we use these different classes of scenarios as architectural test cases to understand, to drive the analysis, to understand the consequences of these decisions, right? We can never know the future. All we can do is make our best guesses at the future and then understand the consequences of those guesses via analysis. So that's one answer. The other answer is, if you build your system with modularity and abstraction and information hiding principles in mind, whatever you build is going to be easier to maintain, easier to modify, easier to evolve. And so we have ways of metrics of measuring the degree of modularity, the degree of decoupling in a system, and more is better, right? In terms of being more future-proof overall.
Yeah. So it comes to the basics that we are taught in the universities, like the solid principles and the other things. Exactly. So yeah. Interesting thing about the exploratory requirements, because I mean, in the book, in the courses on software architecture, I've read about like functional, non-functional requirements, like the technical constraints, but either I missed or it wasn't there about more these kind of exploratory requirements or yeah, asking the questions in that way. So yeah, that's quite interesting. I guess there are way more questions there, but the time is up. So I would like to thank you for sharing your vast knowledge and experience about the topic. And so thanks a lot, Rick. Yeah, I would like to also thank the audience for such an amazing discussion and questions and being active. So you still could write comments under the video. It'll be left after ending of this recording. And also, like, I would like to thank to our army, volunteers, government, people who support Ukraine in these times. And yeah, so thanks for letting us do this stream. So thanks a lot, Rick, and thanks a lot.
Okay, a pleasure. And you know, let me know if you need any more resources or references or anything. I'm always happy to send those along.
Yeah, definitely. I guess people will start asking questions about their sources right after this recording. So I'll maybe reach out to you. So
okay,
yeah, thank you and have a great day.
Thanks. Bye-bye.